Right, so just going straight on. Now we'll do the other case where v, y, it's the same argument with y's with v. Now the second case, that was when v or y has more than one different letter. So it might consist of A's and B's, or A's and C's, or B's and C's, or A's and B's and C's. Okay? But it does not consist only of one of those letters. It's not all A's or all B's or all C's. That was in the case 1. We're now in case 2, where the number of letters is 2 or more, 2 or 3 in other words. Okay? Well, in that case, can you see then that so let v be let v have, say, 2 different letters. So in your substring, so you'll have something like, I don't know, so this is your v, okay, and let's say it consists of A's and B's. So you might have an A here and a B here somewhere, right? So an A here and a B here. All right. Now get a second. Hold on, I'll get 2 pens. So got an A here and a B here, right? That's V. Well, then when you pump it, so we now have another copy of V here. So an A here, a B here, an A here and a B here. Well, that is inconsistent with the pattern of the strings of the language, because the pattern is A to the n, B to the n, C to the n. Right? So all the A's are on the left, and there's no A appearing after the B's. But if you've got an A, B, and then A, B, you've got this A appearing after a B. No. Oh, damn, now which is which? Damn. One of them was dead and the other one was working. Okay. So the order of the A's and B's and C's is wrong. Okay. So and similarly for Y. So we've now got a contradiction in both cases, the 2 cases, where the V contained only one, with substrings of 1 letter type, and the second case when there's 2 or more, 2 or 3. And in both cases we've got a contradiction. Therefore, that string, A to the P, B to the P, C to the P, cannot be pumped. Okay? So we've found a string that cannot be pumped, and therefore the language, we go back to our original assumption, and negate it, and the original assumption was that, what's the language, what do we call it? B, language B. I don't know if you can see this line here. Therefore language B, which we assume to be context-free, we negate that, therefore language B is not context-free. Okay, we've proved it. Alright, that's what I'm saying here. Now, next example. So example 2.37, 37th thing in chapter 2, getting very much towards the end. So now we have another language called C, okay, and its members, its strings, it's a language, set of strings, are of the form A to the I, B to the J, C to the K, and I is going to be greater or equal to 0, and J is going to be greater or equal to I, and K is going to be greater or equal to J. So these I, J, K's, these integers, are assume positive, well, non-negative. They have to be in non-decreasing order. In other words, equal or greater. Right? Going this way, going from left to right. They either the value stays the same or increases as you move from left to right. Okay, so non-decreasing, put it that way, order. So you ask, do the same thing, prove that this language here is not context-free, and we'll do just the same strategies we've done for the other 6 times now, the previous 5 plus the one we've just done. So you use proof by contradiction, assume the opposite. In other words, assume this language C is context-free, and for this particular language there will be a pumping length called little p, whatever it is. Now that we have a clear idea on how to calculate the pumping length for a context-free language, and what was it, the formula? It's little b to the power mod v plus 2. Okay, so this language will have its, each language has its own pumping length, so this language will have a pumping length. Oh, wait a minute, it's not context-free. Alright, well, assuming it's context-free, if it's context-free, it will have its own pumping length. Right? Now, trying to show that this language C is not context-free, it's a little more difficult than the previous case. It's not surprising because it's the second example rather than the first. So, as usual, we find a candidate string that we'll try to prove is not pumpable. Okay, and again, proving, choosing that string is an art. That's where the creativity of the theorem prover comes in. So it's given to you. So let's, and in fact, it's the same. It's the same string, same candidate string as before. So again, it's just A to the P, B to the P, C to the P, where P is the pumping length of this language C, assumed to be a context-free language. And a context-free language, each one will have its own characteristic pumping length. Okay. All right. Now, obviously, the length of this string it'll be 3p, which is greater than p, right? And therefore, this string S can be pumped. So you can split it into 5 sub-strings, U, V, X, Y, Z, right? And we can pump it such that the pump string belongs to the language also. And the pump string satisfies all 3 conditions of the pumping lemma. Okay? Alright, now the one difference in this proof compared to the previous one is in this second example where we are also going to pump down. Can you remember what that means from previous, when we were dealing with the pumping lemma for regular languages? To pump down, what does that mean? It means when you pump down, you can only pump down once. You remove what would be the V and the Y. So what you're left with then would be U, X, Z. Okay, so that's pumping down. Alright, so again, you have the same 2 cases, either the V or the Y. So again, it's condition 2. We're using condition 2 again. In other words, you cannot have both V and Y being the empty string. They cannot both be epsilon. Okay. So let's say V is the non-empty string, and then you have 2 cases. Either the substring V consists of only one type of letter. So it could be just a string of A's, or a string of B's, or a string of C's. That's one case, and just like before, previous example. Or it could be a string of 2 different letters, A's and B's, or A's and C's, or B's and C's. or it could be a string of 3 different letters, all 3 A's and B's and C's. Okay, so again, those 2 cases. Alright, now... Okay, so let's assume then that V consists of only one type of letter. So it's a string of A's, right? And remember the form of the language? It's well, you see it here. Here. Here's the description of the language. Now, if you... So, your string you start with S is of the form U, V, X, Y, Z. Okay? And we're going to pump down. So, we're removing the V. And let's say the V consists of only one type of letter. Let's say the V consists only of A's. Okay? And then we remove that V. Well, that means the number of A's, in other words I here, that I here, hold on. It's more subtle than it looks. Oh, I see. Okay. I'm going to divide it into three subcases. Let's save the bell. Okay, let me recap a little. So let's say the V consists of only one letter type. So maybe all A's, all B's, all C's. And I think we're going the other way. Well, I need to refresh. The actual reasoning doesn't really start to the next session. So I'll stop here and then refresh myself and then continue on with the next session.